Okay, we're going to look at 4.4, which is oxidation reduction reactions. And first thing you got to know is what is a redox reaction. Well, like it says right there in the purple, okay, oxidation reduction reactions are redox reactions, and they are a transfer of electrons. So we're dealing with electrons moving from one spot to another spot. Okay, we're talking about oxidation. Oxidation is when you lose the electrons and become positive. So in one part of the reaction, something is going to be oxidized or go through oxidation, and another part of the reaction, we're going to have to go through reduction. And we're going to explain here this example to the right as to exactly which one's doing which. Because a reduction means that you're gaining electrons and becoming more negative. So one's losing and one's gaining. Okay, so if I look at it, and I look here at my calcium. Okay, calcium doesn't have any charge there that you see. All right, and then it goes and becomes something that has a 2+. So calcium there is the one that went through oxidation. Reduction, on the other hand, I have my H+ here, it's a positive, to becoming one that doesn't have any charge anymore. So it's kind of a 0, we'll look at that later, but that's a 0 oxidation state number. And it goes from a positive to 0, which means it's becoming more negative, so it is reduced. Notice how it's not actually becoming an easy to see negative. You're not going from 0 to -2 or something like that. You're going from a positive to 0, which is moving towards the negative side of things. Okay, one way to try and remember which one is reducing and which one is oxidizing is oil rig. That is, oxidation is losing and reduction is gaining. That's why I always remember which one is oxidized and which one is reduced. So if I go ahead now, we're going to look at two little video clips that are going to help explain oxidation reduction reactions hopefully a little bit better.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
When a zinc rod is immersed in dilute acid solution, hydrogen gas is evolved and zinc ions form in the solution. The solvated hydrogen ion is represented as a hydronium ion, H3O+. In this reaction, zinc is oxidized and hydrogen ion is reduced. When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation reduction reaction occurs. In this reaction, zinc is again oxidized. Now, however, copper 2+ ion is reduced to copper metal. In the two examples we have seen, zinc is oxidized. Because it causes the reduction of other substances, zinc is said to be a reducing agent. The substances that are reduced in these reactions, hydrogen ion or copper +2 ion, are oxidizing agents towards zinc.
Okay, so those are good examples that are showing you what's going on in an oxidation reduction reaction. I like how the ones that were positives got smaller, the ones that were negatives got bigger because you're gaining or losing electrons. I like that. Plus, the second part there is looking at and dealing with a little bit of electrochemistry, which is dealing with when you're plating something when copper or gold or something like that. So we'll look a little more at those later on in the unit here, or actually in the next unit, but this is kind of the beginning for that. So the next one we're looking at here is oxidation numbers. Oxidation numbers, they're at the bottom of your screen. Okay, they help keep track of electrons during a reaction. Okay, when we're dealing with a formal charge, we talked about before, that's when we were assuming everything was sharing. That's what I mean there when I say formal is share. Because formal charge is dealing with just sharing electrons. We break them right in half, and we say you get these electrons, you get these electrons, and we count. Okay, oxidation numbers or charges kind of are the opposite. We assume that nobody shares, and whatever they have is what they have. So just two different ways kind of keep track of these different charges that different elements have. All right, so this big section next is dealing with the rules of oxidation numbers. So I'm going to put up all the rules here, copy them down, and I'm going to roll through what each one is. Okay, so number one, if it's in its elemental form, its oxidation number is 0. So if you see an Mg, a Ca, H2, Na, anything like that, that oxidation number or oxidation charge or charge is 0. Okay. Rule 2, if you have a monatomic ion, that's just the charge of the ion. So if you have something like Na+, and then we know what's the oxidation number of Na+, well, it's just 1+. Okay, if you would have had something that's a 2 negative, the oxidation number of the charge would just be a 2 negative. Okay. The third rule here for determining an oxidation number is that nonmetals are usually a negative number. All right. So they're usually negatives. Oxygen is almost always a -2. Fluorine is pretty much always a -1. If you have a halogen in a binary, meaning HF, Cl, or I, and one other thing, the halogens are always a 1 negative. If you're dealing with a peroxide, which is O2, 2 negative, that means that oxygen is a 1 negative. So peroxides we don't come across very often unless you're dealing with hydrogen peroxide. And in that case, O would have a 1 negative charge, whereas oxygen usually has a 2 negative charge. Okay. Number 4, the sum of the oxidation numbers for a compound should be 0. So if I have 1 positive and 1 negative, it better be 0 for the overall charge of the compound, because the compound shouldn't have a charge. If it had a charge, it would be an ion. Okay. Number 5, the sum of the polyatomic ion is the charge of that ion. So the oxidation number for NO3, the total thing, should be a -1. So when I figure out the oxidation number for N and O, it better add up to -1. Okay. So and then I go with number 6. Okay, hydrogen is a 1+ with a nonmetal and a 1- with a metal. So if hydrogen is with a Cl, it's a 1+. If hydrogen is with sodium, it's a 1-. Okay. So basically, you're just kind of trying to figure out what the charge is for each of these individual atoms, because depending on what they're bonded to, it actually does change, especially when we deal with transition metals. Some elements never change, and others change all the time, especially coppers, tins, lead. Any transition metal will have a lot of different oxidation numbers. So we're going to go ahead here and try and figure out these oxidation states or oxidation numbers or charges for each of the following here. Okay, so we're going to deal with just sulfur. Basically, you start with whatever you're not looking for, assume that is what it normally is, and then we figure out whatever we're looking for. It's kind of how the rule of thumb goes. You pretty much start with the normal ones that never change. You start with either H or Cl or F, something like that. Or if it's sulfur, those tend to be all usually the same. Okay, so we start with one that we're not looking for and assume it is what it normally is. So if I look at hydrogen, hydrogen is normally a 1+. It's with a sulfur. Sulfur is going to be negative here because it's with a nonmetal. So it's a 1+. I have 2 of them, so times 2, so it's a +2. That means to balance out that +2, my sulfur has to have an oxidation state or oxidation number of 2 negative. So the sulfur is a 2 negative. Okay? Sulfur here is S8. Well, there's nothing but just S, so that would be in its elemental form. It's one of the elemental forms of sulfur. So sulfur's oxidation number here is just 0. Okay, go to SCl2. Okay, so looking for S, I start with chlorine. Chlorine is always a -1. Okay, if we're not looking for it, basically. Halogens usually are. It's times 2, so it's a -2, which means in this particular one, sulfur has to balance out that -2, so sulfur here is a +2 for its oxidation number. If I look at Na2SO3, okay, Na is going to be a 1+ times 2, and then I have 3 of the -2s, because each oxygen is a -2 and there's 3 of them, which means I'm dealing with 2 plus a -6, which is -4, which means sulfur then has to cancel out that -4, so sulfur is a +4. Okay, SO4 2-, which means overall I have to add up to 2 negative here. Okay, each oxygen is 2 negative. I have 4 of them, which is -8. I have to end with a -2. So that's where you're going to say -8 plus what? It's going to be -2. And so I'm dealing with sulfur here being a +6. So notice how sulfur's oxidation states there could change very widely based on what it is bonded to.